Okay, geometry 7.6, dilations and similarity in the coordinate plane. So pause and come back and check your work. Remember, when you're simplifying these radicals, what does it mean to simplify them? Matthew? Good, there's no perfect square factor in the radical, but you do not actually estimate the approximate value, right? You leave any non-perfect factors in the radical. So the square root of 12 then would be?
2 squared root of 3.
Good, 2 times the square root of 3. And the square root of 50, Andrew? In number 3, right? So everyone square root of 75? Good, so just a little different than number 2. Find the distance between each pair. And so give me the distance formula. D equals?
2 minus y1 squared plus x2 minus x1 squared.
Okay, so the square root of?
Oh.
Yeah, right, don't forget to say the square root of. Okay. Okay, so 2 square root of 13. So today we're going to apply similarity properties in the coordinate plane, and then tomorrow you'll use coordinate proof to prove figures similar. So we're still talking about scale factor, and today we're going to use it with dilations, okay? And so what is a transformation that changes the size of a figure but not its shape? Jenna? Okay. Doesn't change the shape, so what can we say about an original, a pre-image, and the new figure? If the shape is the same, it's similar, which is what we've been talking about, right? The pre-image and the image are always similar. We just have proportional relationship with the sides, right? What describes how much the figure is enlarged or reduced, Kaylin?
Scale.
Good. So for a dilation with a scale factor of k, you can find the image of a given point by multiplying each of the coordinates by that factor k. So here's a scale factor k. Here's the original, right? And we're going to find the image by multiplying each of these values by your scale factor. So this is kind of common sense. If the scale factor of a dilation is greater than 1, what happens? Like to an entire, let's say a polygon, like a triangle. If you have a scale factor greater than 1 for each of the vertices, then you would have, what do you call that when it gets like that? You're making a sign like these are getting bigger. We call that, it feels like a stretch. And we can also call it, like they do in photography, an enlargement. And if the scale factor is less than 1, what did we call that with our graphs last year? We called it a shrink, right, rather than a stretch. But yes, when it comes to an entire figure, we would say a reduction. So this is just like in photography. We can enlarge things or reduce things. It's more than just a line like we saw last year. So I think I left a lot of this open for you, but let's walk through it. If you're asked to draw the border of a photo with a dilation of scale factor of 5 halves, what will you do? How will you draw the border if we dilate this by 5 halves? By the way, is this greater than or less than 1, this factor? It's greater, it's really 2.5. So this figure is going to look enlarged, right? It's going to be an enlargement. So how would you do it? Don't look ahead. Think, use your brain. What would you do? Michael?
Multiply at point 5.
Right, multiply each point. So you're going to have to go name these vertices and then just multiply each of those values in the ordered pairs by 5 halves. So that's what we see on the next slide. Here is the original rectangle. And you would literally, didn't I leave this open for you or no? Okay, you would literally multiply each coordinate by the scale factor. It doesn't change A because A is at the point of origin, right? And it does change B because where was B? It was A on the y-axis, right? and C and D. So once we have the ordered pairs, we can go graph, and there's an enlargement of the original. And we can call that an image of the original too, right? Remember that term? So, okay, so what would happen to to a photo that was dilated by a scale factor of 1/2? What would be different? Reduction, it's going to bring it down. Notice that the point A at 0, 0 is going to remain there, right? It's going to just shrink down like you're used to seeing sometimes when you've probably grabbed and stretched and shrunk things on your computer, right? So I think I left this open again. Oh, I closed it? Okay. So can you go ahead and apply this scale factor of 1/2 to the coordinates of this rectangle? And we just said that A would be at the same location because A is at 0, 0. So that wipes out the scale factor. Where would B be, Kara?
0, 2.
B prime, I guess I should say. Good, 0, 2. And where would C and C prime? Andrew? D. D would be, Matthew?
1.5
And 0. Good. So now you could go plot those points, and then you're going to see this new, small, reduced, image. Okay? Okay, so be prepared to graph in your assignment. The second way you're going to use this today is to find coordinates of similar triangles. So we are told here that triangle TUO, I always like to go trace that when we get that, right? TUO is similar to triangle RS. Oh, do you even see an S? Oh yeah, this is S here. No, this is S, see? They actually labeled it correctly. The Y is the axis here. So RSO, okay? Yeah. So since these are, we're told similar, can you find the scale factor? How would you do it, Jenna? Okay, and which sides are the easiest to use?
The straight lines.
Right, so the horizontal, we can see these segments really clear. It's easy to see their length, right? And same with the vertical. So how would you set up your proportion?
RO over TO equals OY over
And OU is the missing, do we know that? We don't know that, do we?
We don't know.
We don't even need to know. We just need to find the scale factor, right? So we can do that actually by comparing RO to TO, right? Interesting. So we can substitute the values we know. 12/9 equals 16 over the unknown. We can find OU, right? What would we have to multiply by, or how could you find this?
Couldn't you just find the transformation between T and R? You don't need to.
Between, okay, so they use your cross products to solve for OU, and if OU is 12, we have two ratios that are equivalent, and the question is, what do you multiply by? Find the coordinates of U. Oh, okay, so that's why they're finding OU. So what are the coordinates of U? If OU is 12, this is 0, 12. Okay, and then find the scale factor. How do you go from 0, 12 to 0, 16? You understand? Right? Or how do you go from negative 9, 0 to negative 12, 0?
That's what I'm saying. Can't you just see that negative 9 to
Negative 12.
That's all you need.
But no, you also need to look at the 0 because the 0 wipes out the factor, right? But we do move from 12 to 16 here. So, well, I guess they're using the same scale factor for both coordinates. So what is the factor that we're multiplying by? How do you get from negative 9 to negative 12? And then do you also get from 12 to 16? Okay, so you can set that up if you want the way they did. Going from 0 to 0, 16 to 0, 12, we would multiply by 3/4. right? And we can show that going from, am I taping, -9 to -12, we would multiply, or actually, we would be going the other direction, wouldn't we? 4/3 or 3/12. Depends on which direction you're going,
Yeah.
okay? They're going from 0.16 to 0.12, so it would be 3/4. You said 1 1/3, but you were going the opposite direction, which is true. Okay, so if we're given that triangle MON is similar to triangle POQ, and we're given these coordinates, P, M, and Q, what would the coordinates of N be, and what is the scale factor? So come back and check once you've solved. With the X coordinates from the two given values, right? -15 times what equals -10? And so you divide both sides by -15 and you get 2/3 again. Scale factor is the same for both. Okay? So go ahead and come back when you're ready to check. 80, good job. Find the coordinates of M and the scale factor. Okay, so our scale factor 5/2 or 2.5, and the coordinate is 0, -5. Okay, not a long assignment. Good job.